Hello everyone, this is Borui from Zhejiang University. Today, I will present LinkLab 2.0, a multi-tenant programmable IoT testbed for experimentation with edge cloud integration. This work is accomplished together with my colleagues from Zhejiang University and Alibaba Zhejiang University Joint Institute of Frontier Technologies. Nowadays, developing an IoT application contains many aspects. Here is an example. The user would like to control the smart TV and light at home through a voice assistant. Such a simple application involves the interaction of cloud, edge, and IoT devices. Building such a simple application is not easy for ordinary end users because there are so many devices and cloud services to choose from and provision. They have to own specific hardware, register a number of accounts from typical device vendors or cloud services, and go through their documentations before finally making all things work. Then why not use an IoT testbed? An IoT testbed could provide a wide range of provisioned IoT devices. Users do not have to purchase and set up the IoT devices. Instead, they can simply choose one and begin their programming work. There are already a number of IoT or wireless testbeds across the world, including Fate IoT Lab, MultiLab, Cosmos, and so on. These testbeds target different scenarios. Expect from wireless sensor network, TutorNet targets on low-power wireless sensor network. The devices they provide mostly are energy-constrained IoT devices such as Testbed and Kaijie. Smart Container is a city-scale experimental research facility. Cosmos, on the other hand, focuses on advanced wireless technologies such as millimeter wave. Unfortunately, few of existing testbeds provide cloud and edge support, which makes it hard for building current cloud edge IoT integrated applications. Also, none of existing testbeds support online compilation. Users need to upload compiled binary code to the testbed. That is to say, users still have to build a local software development environment such as cross-compilation toolchains for different devices. In terms of sensing capability and architectures, Smart Container has deployed a wide range of sensors across the city, so it has a superior sensing capability, while Cosmos mainly provides programmable software-defined radio nodes, which falls short in this aspect. In terms of instruction set, Fate IoT Lab gives a more comprehensive support, including 4 architectures. To sum up, existing testbeds have limited support for edge cloud devices or services, do not provide online compilation, and have limited sensing capability and heterogeneity. In this work, we propose LinkLab, which targets cloud edge IoT integrated applications that have sufficient edge cloud support, provide faster online compilation, good sensing capability, and more heterogeneous devices. At high level, LinkLab has 4 design goals: scalable management, multi-tenancy, IoT edge cloud integration, and high reliability. The first one is scalable management. LinkLab was publicly available since the COVID-19 pandemic. During the pandemic, there was a sudden surge in both the number of registered users and the device usage hours, which caused the need of high scalability. Specifically, scalability of LinkLab has 2 aspects, that is, scalable to heterogeneous devices and bursty user requests. For the first aspect, there are already a large spectrum of devices in the cloud, edge, and IoT, and there will be more in the coming future. LinkLab should be able to easily integrate and support new devices. The key enabling module to support device scalability is called the LinkLab Device Center, namely LDC. Designing LDC has several challenges. The first is how to provide a stable and unified interface for other components of LinkLab on top of heterogeneous devices. Second is how to efficiently manage a lot of geographically distributed devices. To address those challenges, we employ a multi-tiered design of LDC. At the top level, LDC controller coordinates the requests and hardware resources. In the middle, LDC servers are deployed on the servers near to the devices and are responsible for various functionalities such as device assignment and code compilation. At the bottom, LDC clients are responsible to manage the heterogeneous devices and provide a unified management interface for LDC servers. To improve the resource utilization, LDC clients are actually deployed on edge devices with moderate computing capability. For the second aspect, to deal with bursty user requests, we first present the workflow that how LinkLab processes a user request. There are mainly 4 steps: server allocation, device allocation, code compilation, and device programming. According to our operational experiences, when dealing with bursty user requests, we run into bottlenecks during all these steps. Specifically, some components will suffer from CPU and RAM bottleneck, causing longer processing delay or even out-of-memory queues. Hence, we containerize these services for auto-scaling, which allow LinkLab to properly scale up and down resources for different services. We take the bottlenecks when compiling codes as an example. Originally, we place the compilation services only on LDC servers. However, we noticed that the programmable edge devices and LDC clients for IoT devices may idle. Why not use them to help compilation? Moreover, the architecture of these edge devices are different, so we employ a heterogeneous container scaling mechanism to make full use of all free devices. We dynamically build the service image for each architecture and use cgroup to isolate between scaled services and user tasks. This is how LinkLab deals with the scalability of devices and user requests. We then move on to the second goal of LinkLab, multi-tenancy. LinkLab also includes several subsets operated by our cooperative universities. However, considering this situation, you are one of the students of LinkLab subsets and you are finishing your coding task of your final exam. But the devices are all occupied by others. This is a really desperate situation. So subsets and some special user groups of main site require timely execution during class time or examination. Toward this problem, we first propose a structured configuration for the administrators of LinkLab to specify their requirements. The hardware are divided to exclusive and shared mode. The administrators also could set the available services and their concurrency of each tenant. For example, in the last figure, we create a tenant named G1, which has 80 exclusive Arduino Mega boards, and also set up services quota for each services of G1. To realize the tenant configuration for the management services of each new tenant, our containerized design is a solid foundation, and we only need to audit and restrict the resource usages of each tenant. In addition, LinkLab is not only composed by services, but also devices. We must also design a multi-tenancy mechanism for devices. The naive approach is a fixed partition, which definitely leads to low device usage. What if we preempt other execution for running the task of the user of that tenant? This will lower the QoE of other users. Then how to achieve device-involved multi-tenancy with high device usage and user experience? We have an observation that LinkLab could foresee the concurrent usage of devices. This is because LinkLab integrates these coding, compiling, and programming steps of IoT development, so we can use these user footprints to predict the future device usage pattern of each tenant and reserve devices in advance. According to this observation, we apply this dynamic reservation mechanism in our system. We then test our device-involved multi-tenancy with 2 tenants. As showed before, we create 2 tenants in our main site. G1 has 80 exclusive devices and G2 has 20. We can first see that when the concurrency is small, the average latency is also small. When we increase the request pressure of G1 that exceeds the tenant limit, we can see that the latency of G1 skyrockets, but the latency of G2 is still low, and vice versa for the G2. This experiment is a representative case to show the effectiveness of our device-involved multi-tenancy mechanism. You can find the description of other design points of LinkLab in the paper, and we omit them due to the time limit. LinkLab was not built in a day. We started building LinkLab from 2019, and we separate the building process to 3 phases. In the first phase, as you can see, LinkLab only has 60 IoT devices, and we focus on the basic building blocks of LinkLab, such as device management, online compilation, and the web-based IDE. In the second phase, based on our experience in IoT application development and the requests from LinkLab user community, we started to notice the necessity of integrating IoT and cloud edge devices. In the third phase, the COVID-19 brings many users, so we reconstructed LinkLab to better serve the bursty user requests. Moreover, we also add some realistic scenarios such as office area BLE mesh deployment. Up to now, LinkLab has over 500 devices, including nearly 450 heterogeneous IoT devices, over 80 edge devices. Some of them are with AI accelerator such as NVIDIA adjacent, and a programmable server with GPU support. With LinkLab, users could hands-on several research domains, not only including cloud edge IoT integrated application, but also the traditional ones such as IoT networking protocols and the newest ones such as container-based IoT and serverless computing. During our 4-year operation, we closely work with educational institutions, commercial operation, and third-party individuals to extend the border of LinkLab. For example, we apply LinkLab to a fieldwork course of a college which is proficiently training IoT developers for the local smart elderly care industry. LinkLab offers an online-offline integrated toolkit toward this specific scenario. The students could learn and practice IoT programming with a 3D visualized scenario in LinkLab and actually deploy the sensors and actuators with the tabletop model with real hardware. To recap, we introduced LinkLab, a multi-tenant testbed which integrates the cloud, edge, and IoT deployment. Up to now, LinkLab has attracted over 2,000 users who conduct over 17,000 hours of experiment. LinkLab is also a publicly available service that is accessible here at linklab.mnes.cn. We are kindly welcome the new users and feedbacks from all over the world. Thank you for your time, and we are ready for your questions.